All right, so I hope you enjoyed your nice analytics section with zero graphs, exponential functions. Now we're going to start talking about graphs. So again, this really ties back to chapter 3, composition of functions and inverse functions. So also go back 2 sections to 6.2. Remember what exponential functions look like, 2 to the x, okay? What we've got here is some function that looks like this, with a y-intercept of 1. It keeps doubling. As you increase x by 1, the function doubles. And as you decrease x by 1, the function gets cut in half. We've got this asymptote right here. It gets very close to the x-axis, but never touches. Now remember that one of the big things we talked about when we talked about inverse functions is that the graph of an inverse function is found by switching your x's and your y's. Okay? It's also the same as reflecting across this dotted line. So look, if I reflect this function around this dotted line, that's going to give me the graph of the inverse. Okay? And we know the inverse of an exponential is a logarithm with the same base. The base of the exponential is 2. That'll be the base of our logarithm. So this is what logarithmic graphs look like. They're like exponential functions that just got reflected a little bit because they're inverses. So just switch all the x's and the y's and you've got yourself a bona fide logarithmic graph. Okay. Also remember that, again, 3.7 is huge. Go back and review it. Look at some of the homework problems. Watch the videos again if you need to. It's going to help a lot in this chapter. Okay. And one of the things that we said there is that the domain of a function is the range of its inverse. Okay, the range of the logarithm is all the y values for the logarithm. So the range of any log function is all real numbers. We cover every y value, as small as we want of a y value and as big as we want of a y value. Okay? And the domain is all the x's. And again, the domain of the inverse function was the range of the original function. That's going to be 0 to infinity. And then again, remember for exponential functions, we had the asymptote being a horizontal asymptote, usually the x-axis. Well, if you flip that sideways, we now get a vertical asymptote for logs. It gets really close to the y-axis, but it never actually hits it. And these are some of the things that we're going to be talking about a lot. And it appears as if the sun is shining through my window off of the snow and giving us a nice glare. I'm going to make this a little easier for you guys to see. All right. That doesn't look to have done anything. So that's what we're going to be doing today. We're going to be graphing functions and talking about domain and range. And specifically, before we get into some serious graphing, we're going to talk about domain and range right here. All right, so, oh, and one more thing, right, is normally we talk about the y-intercept as just being 1. Well, here, the x-intercept of a usual 1 is 1. But again, some things can happen to change this a little bit. So example 1. Find the domain and the range for the following. Part 1. Y is equal to log base 3 of x plus 4. Now, just like with exponentials, I said the domain of an exponential function is all real numbers, always. There's no exponential function you can give me that doesn't have a domain of all real numbers, unless you do super wacky things that are outside of this class. And then it's not really an exponential function anymore. All right. Similarly, the range of any logarithm is always all real numbers. So I'm just going to, right off the bat, any problem, range of this logarithm, all real numbers. I don't even need to look at the logarithm. The range is going to be everything, at least in this class. Okay. Now for the domain, normally the domain is 0 to infinity. But we're transforming this guy. This thing is getting moved left 4 units. So it's not going to be 0 to infinity anymore. It's going to be -4 to infinity because it got shifted. Another thing to remember for here is remember domain in general. We've talked about domains of a couple functions, right? So one of the things that we talked about was the domain of a rational function, right? If we've got stuff like this, the domain of this is when the denominator is not equal to 0. We talked about square roots or fourth roots or sixth roots, a root with an even index. Remember, we said the domain here is when the inside is greater than or equal to 0, because we don't want to get complex numbers right here. So if it's 0 or bigger on the inside, then we're real. That's what we did for the domain here. Well, for logarithms, we need the inside to be strictly bigger than 0. We cannot take the logarithm of a negative number. We cannot take the logarithm of 0. And the reason why is because exponentials never hit those numbers. Exponentials never hit 0. Exponentials never hit negatives. So that's where this requirement comes from. So this is how we're going to find the domain of a logarithmic function. Okay. So our domain here, let's leave a little blank for it and box our answer. We just got to put something in the box. All right. It's like wrapping a gift before you bought the gift. Don't do that. So we need the inside of this logarithm to be positive. Inside of the logarithm is x plus 4. Subtract 4 from both sides. You're going to get x is greater than -4. So -4 to positive infinity. That's our domain. Again, it's just the domain of any logarithm. If it's just a normal logarithm, will be 0 to infinity. But we shifted this one over left 4 units. So now it's -4 to infinity. And other transformations can make this a little messier, but you'll never go wrong if you make the inside greater than 0. All right. Let's do another one. Y is equal to log base 5 of 2x plus 9 minus 2. This one looks messier, but just we do it the same way. Range. Now I'm looking at the function. This is the range. All right, I can't write math without looking at my paper. I was trying to make a point here. The range of any logarithm is -infinity to positive infinity. Okay. The domain takes a little bit more work. And remember, -infinity to positive infinity is the same as writing an R like this. These are equivalent. I probably would have had better luck doing the R without looking. For the domain, we need the inside of the logarithm to be greater than 0. The inside of the logarithm is 2x plus 9. So we just find when this is the case. Subtract 9 from both sides to get 2x is bigger than -9, and divide both sides by 2. X has to be bigger than -9/2. We'll say -9/2 up to infinity, like so. And again, if you want to use set builder notation, the set of all x such that x is bigger than -9/2, this is perfectly okay as well. I usually just use whichever one requires less writing. For a lot of these, that's going to be interval notation. But I'll take this. This is A-okay. All right. Let's do one more, and then we're going to be done for this video. Nicely enough, these videos aren't going super long today. Nobody likes watching a long math video. That's not true. I'm sure somebody out there does. F of x is equal to log base 2 of 12 minus 3x minus 3. And, let's add a negative before here. And, it doesn't matter. It doesn't matter because the range is always the same. Any logarithm has this range. Okay. The domain is where we got to work a little bit. And again, it doesn't matter. All this stuff's happening. I don't care that there's a negative out here. I don't care that there's a -3 here. For the domain, all I care about is what are we taking the logarithm of? Because that thing on the inside needs to be positive. Okay. So subtract 12 from both sides. Divide both sides by -3. Remember, whenever you multiply or divide by a negative, the inequality switches directions. We're going to x is less than 4. In this case, we can actually plug in negative numbers. Because when we plug in a negative number, it'll become positive. All right, and that's domain and range. And that's logarithms. We're in next video, we're going to talk about asymptotes and intercepts. In the final video, we're going to get into graphing. Okay? Good luck with these problems.